Hey, 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 how's everyone doing? Let me know if you can hear me. Perfect. All right, any general questions before we get started on this? The link is in the chat and also the description box below the video. It's a Dropbox link, so you can download the blank copy and the solutions to it if it isn't already posted online. So, any general questions before we dive into it? Or are we all good? All right. So let's run through this practice exam. So this one actually has 6 questions on it. That's mainly because I actually put more content on a couple of the questions to kind of compensate for a lack of a question. So it's in a sense like having 7 questions on this. There are some things that are similar to the first practice exam due to the time that I've had. But also some new concepts. I especially tried to spend a lot of time making it at least 1 or 2 brand new problems, so mainly the one on the cover. So if you're a little bit more into astronomy, then you'll like the first question, certainly. All right, let's get started on this then. So this first question, neutron stars are some of the densest collections of matter in the known universe, formed by the inward collapse of star cores, having both intense gravitational fields as well as unfathomably strong magnetic fields. Consider that the sun, which I give you the mass of the sun, as well as the radius of the sun, were to completely collapse into a neutron star whose radius is only 10 kilometers, compared to 696,000 kilometers. Given that the sun rotates about its center through one revolution every 25 days, and assuming the mass is conserved, we're going to do the following. So the first question I want to know is, what is the ratio of the moment of inertia of the neutron star, so moment of inertia I of the neutron star, compared to the sun's moment of inertia, call it I. So we're going to find a ratio between those, and then we're also going to find out how the angular speed of one compares to the other. Let me know if the video looks okay. Give me a thumbs up in the chat, or let me know otherwise. So, for this problem here, we have so there's the sun. Here's the sun, and it spins about its center with an angular speed omega. And we know that the mass is 1.99, 10 to the 30th kilograms, and its radius r is 696,000 kilometers. Okay. So what we're going to do is we're going to assume that this entire ball of mass, so you can model it as a sphere, is going to collapse completely into basically this really tiny sphere. And so here's that tinier sphere. It's also going to spin, but we're going to call that angular speed or angular velocity something different. So you could go like omega 1, omega 2. In this case, I'm going to call it omega prime. And now we know that the mass is conserved through this. There's no loss of mass. I tell you to assume that in the problem. So the mass that we take for the sun is going to be the mass of this, just packed into a tighter space. So the mass, call it m prime, is equal to the mass of the sun. Now the radius is drastically different, call it r prime, is only 10 kilometers. So assuming that this is a closed system and nothing else is going on with this, this is kind of like an ice skater example where they bring their arms in and something happens. If you have an idea of what principle is applied here, shout it out in the chat. I'll give you 15 to 20 seconds to think about it. Shout out that concept if you know exactly what this is that's happening. Any ideas of how we approach this problem? The hint is to think of it like an ice skater bringing their arms in. Yep, it involves inertia. There is a core concept that actually uses the inertia to solve this problem. What is that fundamental concept that solves the problem using inertia? So the moment of inertia decreases. Yeah, it'll be the moment of inertia of a sphere. The moment of inertia decreases, causing the angular speed to actually increase in exchange for that. So this is actually the conservation of angular momentum. So for instance, with the ice skater, they spin around with their arms out, and they spin at a slower rate. And as they're spinning around, they bring their arms in, they move faster. So it's a conservation of angular momentum in this case. So the conservation of angular momentum states that the total angular momentum of the system initially equals the total angular momentum final. So we say the angular momentum, L, we're going to say in general is the moment of inertia, I, times omega. So we're going to say then that I omega equals I prime omega prime. So the moment of the angular momentum initially equals the angular momentum final. So whatever it is for the sun equals whatever it is for the neutron star. Now, in our case, I want to first figure out what the ratio of the angular momentum is. So what I'm going to do is I'm going to write the ratio, which is I prime over I. Whenever you're taking the ratio, you just divide one by the other. Another way I could phrase this, instead of asking you for the ratio, is I could ask you how much bigger or how much smaller is one compared to the other. So this is just a way of saying how much bigger or smaller is the final moment of inertia compared to the initial moment of inertia. So since it's a sphere, we know it's 2/5 mr squared, but for the neutron star after, we're going to put primes on everything. So 2/5 m prime r prime squared. And we're going to divide that by the original moment of inertia for the sun, which is 2/5 m r squared. Now, when we take this ratio, a lot of things will end up canceling out because they stay constant. So for instance, 2/5 doesn't even matter there. The masses are actually the same in this case because we're assuming in this problem that the mass is conserved or does not leave the system. So the mass of the sun is the same as the mass of the neutron star. So they're also the same, so they just cancel out. Now, the radii are different, so that's all that's left. So we have r prime over r squared. And we just plug in each of the two radii. So we just say that the radius of the neutron star is 10 kilometers. We can leave it in kilometers because they're both expressed in kilometers and they just cancel out. So it's 10 over 696,000. You could put it in scientific if you wanted to. Take that ratio and don't forget to square it so that you get the ratio of the moment of inertia end up being, calculated this earlier, it is 2.06 times 10 to the minus 10th. So what this statement means is that the moment of inertia of the system after, so the neutron star, is this amount times what it was initially. In other words, it's much, 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 much smaller. It's 10 to the minus 10th times smaller. Let me know if you have any questions up to here before we apply the conservation of angular momentum to solve the latter half of this question. So what the answer really means is, okay, so let me actually rewrite this. If you just move the moment of inertia from the bottom over to the other side, this also reads I prime equals 2.06 times 10 to the minus 10th times the original moment of inertia. So the moment of inertia after equals this number, which is really, 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 really small, times what it was originally. So the moment of inertia got many, many times smaller because it's a number that's much less than 1. So for instance, if this number were 0.5 or a half, then I would say, oh, the moment of inertia cut in half. Or if it was 0.25, I would say it's 25% of its original value. But in this case, it's much smaller than that. So that's what it represents. Hopefully that answers your question about that. Whenever you take ratios, that's essentially what you're saying in a ratio. Now what I'm going to do is answer the latter half of this question, which is actually asking for what the ratio of the two angular speeds are. So what it is after compared to what it is before. So this is where we actually apply the conservation of angular momentum here. Make sure there's no other questions. Okay, so this is where we actually apply the conservation of angular momentum. Is in order to find out what the angular momentum is after to what it was before, I need to just solve for that ratio. An almost equivalent question to this is I could just simply ask you for what the final angular velocity or final angular speed is, and you would just calculate that using this and just solving for it. But instead, you're just going to solve for the ratio. So in other words, I'm going to move this over to the right side, the angular speed initial, divide it off over to here, and then I'm going to divide off the moment of inertia prime to the other side. So what this says is I over I prime equals omega prime over omega. Okay? So I've solved for the ratio basically. Now, this essentially right here is what I'm asking for in the problem. What that angular speed is after to what it was before. So all I need to do is plug in the ratio of the the ratio of the moments of inertia, but the difference is that it's upside down, it's flipped. So all you do is you take this number and you just invert it. So in other words, omega prime over omega is equal to 1 over the value you got, which is 2.06 times 10 to the minus 10th. And you find that this ratio ends up being 4.84 times 10 to the 9th. In other words, what this means is that the angular speed of the star after the neutron star equals 4.84 times 10 to the 9th times larger than the original angular speed. Let me know if that makes any sense or if you have any questions on how I solved part A to get to this. So far, so good. Now, this problem is actually a realistic problem, so if you ever get curious about the universe, go look up neutron stars. This is actually a thing that happens. The angular speed drastically increases when the star collapses down, so... I spent a lot of time trying to make sure this problem was actually accurate to the real thing, so you are actually solving a real-life problem, more or less. And if you come by tomorrow in person to the last review session before the test from 12 to 2, I believe, if I'm remembering correctly, if you come in person, we'll do one more practice final version, and we'll do even more fun stuff. And I will apparently bring chocolate candy and Skittles and stuff, so be sure to drop by in person. Now, I want to know, part B, what is the angular speed of the neutron star in revolutions per day? So the previous part here was basically solving for how much bigger or smaller the new angular speed was compared to what it was before. Since you now know how many times larger it is, all you do is you take the original angular speed, which I tell you that the sun rotates one revolution every 25 days. So that is its spin rate or its angular speed. So we just take that number and we multiply it by the factor that we get from part A to say, oh, it's that many times bigger. So let's do that real quick for part B. So let's write that the angular speed final, actually I wrote it right here, is 4.84 times 10 to the 9th times the angular speed initially. From that statement saying that's that many times bigger, all I do is I just drop in what the angular speed was initially. So now it's 4.84 times 10 to the 9th times the original spin rate of one revolution, abbreviate 1 rev, per 25 days. Put that all together, calculate that out, and the answer you get for that is that the final angular speed or spin rate of the star is 1.94 times 10 to the 8th revolutions per day. For an estimate of what that is, 10 to the 6th is 1,000,000 times. So this is actually, the star is spinning 194 million times per day. That's really, really, really fast. The Earth only spins once per day. So we have this really, really high spin rate. I also want it in revolutions per second. So all we do is we convert the days into seconds. So you could do that if you know how many seconds there are in a day. There's 86,400 seconds in a day. Otherwise, you can do the step-by-step conversion. Say there is 24 hours in a day. There is 60 minutes per hour, and then you could say that there is 60 seconds per minute. When you convert that, it's also going to be equal to 2,240 revolutions per second. So this star spins at over 2,000 revolutions per second. It's amazing. Let me know if you have any questions on this part of just getting the angular speed value, and then we'll solve the last part. Whenever you're solving a problem, note that these numbers that we're getting for this problem are basically on the extreme end of values you should ever get for a problem, because this is one of the most extreme things in the universe. So on a problem with things like a merry-go-round spinning or any other everyday life things, you should probably expect the values that you're calculating for this problem comparatively should be much bigger than anything you would see on Earth. The last part of this problem is, what is the linear speed of a point on the equator of the neutron star as it spins around? Once we get that speed, I just want what percentage of the speed of light it is. The speed of light I give you here, and we'll just compare it to what the speed of light is and what that percentage of it is. So let's just find that linear speed. So what's essentially being asked for here is you take the surface of the star. So here is the neutron star. So here's our neutron star, and here's the axis of rotation. And there's our spin, omega prime. Here's the equator, right along here. So all I'm saying is if you take a point anywhere on that equator and you watch that point spin around and around and around, how fast is it moving in meters per second, the linear speed? So all the problem really is if you look at it this way, draw the path that it goes in, which is just a circle. So here's the top view. Here's the path that it moves in. It's just a circle. And a circle takes up the radius of whatever the star is. So in this case, we just use the radius of that star. And we ask, oh, how fast does it move in a circle at that radius? That's really easy. The linear speed is just v equals r times omega. In our case, we're just calling everything prime, so it's just v prime, r prime, and omega prime. So the radius of the neutron star is 10 times 10 to the third meters, and it's 10 to the third meters because it's in kilometers. Omega, we found in the previous part. Now, these are all in revolutions. When you are finding a linear speed or a linear quantity based on a rotational quantity, an angular quantity, it has to be in radians. So you will have to make one last conversion to this. So using this number right here, 2240 revolutions per second, or whatever you had in your calculator, we need to put that into radians per second so it's in standard units so that we will get meters per second here. So all you do is you take this value and you multiply by 2 pi radians. You don't technically need to write the unit out, but it's just to emphasize there, per 1 revolution. This will cancel out the units of revolutions, and it will give you radians per second. In that case, when you convert that properly, the value that you'll get is 1.41 times 10 to the fourth radians per second, or 1 over seconds. Put that into here, 1.41 times 10 to the fourth. I'll ignore the radians, so it's 1 over seconds. The units will be meters per second here, and that speed that you get is 1.41 times 10 to the 8th meters per second. This is how fast that point revolves around the equator of the star. And finally, once we get that linear speed, I've just asked a simple question of how much is this compared to the speed of light as a percentage. So finally, all we do here is we take this number and we divide it by the speed of light. So if we take the ratio of this speed to the speed of light, which we call c, it's 1.41 times 10 to the 8th meters per second divided by 3.00 times 10 to the 8th meters per second, given in the problem. And this ratio ends up being 0.47. In other words, therefore, this speed is 47% of the speed of light. The fastest speed that you can go in the known universe is the speed of light. You're going about half of that. And that's why neutron stars are actually one of the most interesting things in the universe, in my opinion. Let me know if you have any questions on any of the conversions I've done, how I got the linear speed, and the final percentage. I'm glad you think it's really cool. That's personally why I actually love astronomy quite a bit. When I do get the chance to study astronomy, this is one of the most interesting things to me. So, how do you get R prime? You mean the radius of the neutron star? That's given in the problem. So actually, here specifically, this value right here for r prime, which is 10 times 10 to the third meters, it's the radius of the neutron star, but I do state in the problem for that. So what I told you actually was not this value verbatim. I actually gave you 10 kilometers. That's the value I gave you in the problem. And then this is just the kilometers to meters, which is 10 to the third. Let me know if that clears it up. Any other questions on this before we move on to the... Well, there's two more parts to this question, so it's a longer question that I made in compensation for not having another problem on this version. So I don't derive anything in regard to the radius. For the radius, that's just given in the problem. But I derive anything, I'm not sure what you mean by that. Let me know more specifically on that. I'm going to start this part D of the question, but feel free to keep on letting me know more specifically on that. Part D, we have what is the gravitational acceleration on the surface of the neutron star? And then how does this compare to the surface of Earth? So Earth's gravity, which is 9.8 meters per second squared. So this one, if you just know the right equation to use, is just plug it in and get the value. So I'll leave this on the right side in case there's anything left on that. Now, the gravitational acceleration on the surface of the neutron star, you can just get by using G equals big G, the gravitational constant, the universal one, the mass of the planet or the star in this case, divided by the radius you are from it squared. This is just the general equation for the gravitational acceleration. Now, if you don't have that for some reason, then what you should have is that it comes from the force equals mg, which is you should know more as the weight of the object. Now, this is equal to big G, big M, little m over r squared, which is the gravitational force between two celestial bodies, such as two planets, two stars, whatever it may be. So when you equate those and you cancel out and solve for the gravitational acceleration, you get this equation here, if you didn't have it already. Now, if you were to plug in the values for Earth, such as the radius of the Earth, the mass of the Earth, the value you're going to get is 9.8. But this equation accounts for how the gravitational acceleration weakens the further you go from that mass, whether it's Earth or the star. Now, in our case, we're going to use it for the star, because we already know what the acceleration on Earth is. We already know it's 9.8. So I'll write this equation for the star. So I'll put everything in terms of prime. G prime is the gravitational constant, mass of the neutron star, so m prime. And then we're going to be on the surface of it, so I'm going to use the surface radius squared. We know the mass because we know it's just taken from the mass of the sun in this case. So we have G, which is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. The mass of the star is 1.99, 10 to the 30th kilograms, and the radius is the radius of the neutron star, which is 10 kilometers, so 10 times 10 to the third meters, and don't forget to square it. Okay. So now, the value for G that we get when we're on the surface of the neutron star, don't try that at home. The value for that is 1.33 times, when I have to write a power of 10, you know it's big, 10 to the 12th meters per second squared. You might be somewhat shocked that this value is so drastically big, but this is one of the most violent things in the universe. It's almost as close as you get to actually a black hole. So the gravitational pull of a neutron star is ludicrously big. And if you compare that to the gravitational acceleration on Earth, well, you just take the ratio. So the gravitational acceleration of our neutron star divided by the gravitational acceleration on Earth is just that value, 1.33 times 10 to the 12th meters per second squared divided by 9.8 meters per second squared. When you take that ratio, you end up getting that it's 1.35 times 10 to the 11th meters per second squared. And that value represents that the acceleration on the surface of that star is that number, which is, if you look at it, it's 135 billion times stronger than Earth. So this was just a plug and chug part of the question, other than just taking another ratio. So, question: what is big M? Big M is the mass that you want to use to compute the gravitational acceleration of that mass. So, for instance, here, when I write this equation, okay. Now, you could have multiple masses in a problem. Like, I could have the Earth, and I could have literally just this, pen that I'm holding, okay? So, I have two different masses involved, the Earth and some object I'm holding. Now, if you get stuck in that situation, well, which mass do I use to compute G? Well, you are asking for the gravitational acceleration of, well, if it was the planet, like, let's say it's Earth, then you would use the mass of whatever you're questioning the gravity of. So in that case, you would use the mass of the Earth. Now in this case, because I want to know the gravitational pull of that neutron star, I just use the mass of that neutron star. And in this case, I tell you it's just the same as the mass of the sun. Isn't M the mass of the sun? Yes. Which I am claiming is the mass of the neutron star, because I told you that the masses remain the same. There's no loss or gain in mass in the problem. The units cancel out, right? Yes, they do cancel out, actually. If you actually look at this a little bit more closely, the units you actually get initially are not going to read meters per second squared. It's good that you are checking your units, because if your units do not work out, then you've done something wrong. You've plugged in something wrong, or you've manipulated the algebra incorrectly. However, if you look at the units of this, so let's say if we take a look at all the units here. So I have, here's the units here, here, and here, but don't forget to square them. If you write those out, the units end up being, in this dimensional analysis, newtons meters squared per kilogram squared times kilograms over meters squared. And after cleaning that up, canceling the meters squared, getting rid of one of your kilograms, the units you get are actually newtons per kilogram by default. This actually means that for every kilogram of mass you have, it's going to exert that many newtons of force on it. So for instance, 9.8 meters per second squared could also be rewritten as 9.8 newtons per kilogram, which says that for every 1 kilogram of mass you have, there is 9.8 newtons of force on it. Now, in the interest of meters per second squared with what you're used to, you can write the newtons as kilograms times meters per second squared, and then cancel out the kilograms, leaving you with what you expect it to be. So the units definitely do work out in the end. How do you know that an answer as massive as this makes sense? I know we were talking about neutron stars, but how do you develop a sense of common sense, quote unquote? Basically, this problem was intended to stretch your limits a little bit, because one of the things that you want to question as, a person either going into physics, chemistry, whatever it may be, is that whatever you're looking at makes sense. If it doesn't make sense, you're supposed to question it, and you're supposed to double check it, triple check it, quadruple check it. And the thing is that when you, let's say you go into research and you try to contribute something to your field, let's say you want to go try to make a discovery or something, well, sometimes maybe things won't make sense. And you have to figure out why it doesn't make sense and then make sense of that. So what I'm doing here essentially is I'm broadening your horizon to help you get a better range of what things can be based on the scale that you're working with. So for instance, if you go more towards the astronomy route, if you choose to go into astrophysics or something, then things are much more on the extreme scale in the universe. You have large bodies, then you have large amounts of force. You have large moments of inertia. You have, in this case, super massive gravitational accelerations that are way beyond the scale of what you would see on Earth. So this gives you the high end of the scale. So if you find numbers that are larger than this, it probably will happen less than 1% of the time, because this is such an extreme end of the scale. You could similarly go down to the microscopic scale, and then you can develop an intuition for what happens on the microscopic scale. So once you get all the astronomically large stuff and all the microscopically small stuff, that will give you your range of what the possibilities are. So long story short, TLDR, I'm just basically developing your common sense. You may not quite have a full set of what exactly should be common sense for numbers. This will just broaden that. So do I expect you to know that this was the answer? No. This is more to actually just impress you and wow you. So I'm confused as to why you use the derivative symbol. The prime. The prime is used as the derivative symbol in calculus, however, is not a derivative in this problem. I think I see what you... Oh, that's what you meant earlier. You said derivative, not derive. Let's see. Oh, no, yeah. Okay, so you said derive and then you said derivative. Yeah, so when I'm using the prime here, which actually, as you go and do more problems and stuff, other places will also use prime in some notations. Prime doesn't have to mean derivative. If you're talking in strictly a math context, it's often used as a derivative, but in general notation, sometimes prime is just a way of saying that's basically the same quantity, but for something else. Just treat it as instead of m and m prime, it's a mass 1 and a mass 2. So there's no derivatives or anything. And then we have a last question on this. If you have any other questions, still feel free to drop them. The last question on this problem 1 is, what is the minimum speed needed to escape the gravitational pull of the neutron star from its surface? Now, this word already should kind of tell you where you're supposed to go with this, but even without that word, if I'm asking you for a speed or velocity needed to basically get away from a mass, you should recognize that as the escape velocity, or in the words of Finding Nemo, escape. Now, in this case, I don't want you to just use the formula. I want you to actually conceptually and algebraically understand what you're doing with the formula. So how does the formula work? Where does it come from? So in other words, what I want you to do here is use a physical principle that you know how to use and apply that principle and then reach the solution. In that process, you will end up coming up with an escape velocity. So here's what I mean. I'm glad that cracked you up. Now, the principle that you want to use here to solve this problem, to get the escape velocity, is, now you could think of it as, okay, so let's think of it as if you were to be on Earth. On Earth, if I ask you to find the velocity needed to escape the gravity of Earth, what you would need to do is you would need to take some object and you would need to throw it up with fast enough velocity so that it goes high enough that it basically never comes back down. Now, I could never do that, but we do that all the time with things like rockets, or, Elon Musk goes launching his, roadster into orbit around the sun, whatever it may be. But in this case, I'm just going to ask the same question for the neutron star. So what you do is you could think, okay, well, if I have some initial velocity, I'm going to go through some height. It kind of has a kinematics feel like to it, but anywhere you would want to use kinematics, remember that you can always apply conservation of energy. That's exactly what we're going to do in this problem, because conservation of energy actually makes this much simpler, because what happens is, as the object goes higher and higher and higher, the gravity gets significantly weaker. So you have to account for a changing value of the gravity, which is not going to work well with your kinematic equations. You have to use calculus on that. Now, conservation of energy, it doesn't care about all the details in between. It just cares, what do you have to start with and what do you have to end with? Nothing in between. Now, here, we would just say, oh, by conservation of energy, assuming that there are no non-conservative forces at play, such as friction, being one of the main ones, I could just say that the total mechanical energy to start with, in other words, kinetic plus potential, equals the total mechanical energy I have to end with, which is also kinetic but final plus potential energy final. Now, in here, your kinetic energy is going to be the usual 1/2 mv squared, because you just have a point mass and you throw it up and it moves linearly, so it's just the linear kinetic energy, which is 1/2 mv squared. Now, the potential energy, though, you can't just write as mgh or mgy, because that value is for that equation is for a constant value of g, which is continuously changing. So it doesn't quite work so well there. You need the more broad definition of gravitational potential energy, which you might recall is the gravitational potential energy is minus big G, the mass of the planet or the star, whatever it is, times the mass of the object that you are throwing upwards, whatever it is, so what we use little m for that, and then divided by the radius, not squared in this case. So this is the more broad definition of the gravitational potential energy. Now, when I plug all those into here, so for instance, I write kinetic energy is 1/2 mv initial squared. I'm going to use little m here because this is regarding the kinetic energy of the mass that I'm throwing upwards, which is little m, plus the initial gravitational potential energy, which is this expression with the minus sign, so you write minus big G, big M, little m over r. Now, I'm going to argue that this radius here is just the radius of the planet or the star in this case, so I'm going to write capital R, or r prime in our case. You could also say that the mass of the star or the planet, big M, is M prime in our case, because it's the neutron star. This is equal to 1/2 mv final squared. So again, kinetic energy of that object that's moving linearly, plus gravitational potential energy, again with a minus sign, minus big G, big M prime, little m, over. Now, here we are not going to be at the radius of the planet anymore. We're no longer on the surface. We are way, way, way out there somewhere. Now, that distance has to be technically infinitely far away, so to infinity and beyond, if you will, in order to truly escape the gravity of the planet, theoretically. So we'll call it lowercase r for now. It will be basically infinity. So with that said, because we need to go to infinity to escape the gravity of the planet, we plug in infinity into the bottom, or we take the limit as it goes to infinity, rather. And any number over infinity will be 0. So this term right here drops out to 0. Okay, and that's because r goes to infinity, to escape. All right, so this term drops out. Now also, when you have escaped, ideally, well, I guess not ideally, the minimum scenario you would need is that it reaches, it basically runs out of kinetic energy at infinity, basically. So you have just barely escaped it. So at infinity, you should also have that it's not moving by that point. So that term also drops out to 0. From here, you just solve for your initial velocity. So we have 1/2 mv initial squared minus big G, big M, little m over the radius of the planet equal to 0. Move the term over, so it's 1/2 mv initial squared equal to big G, big M, little m over radius of the neutron star. And at this point, you can clean it up a lot and just solve for v. So for instance, you can get rid of the mass, little n. I never told you what the mass of the object you were throwing was, because it doesn't matter in this case. Whatever mass that object you were throwing has, just cancels out. All you have left at the end of this, when you solve for that initial velocity needed to escape the gravity of the star, v initial equals, we will multiply by 2 to both sides, and we will square root both sides to isolate the velocity. So it's the square root of 2 big G, big M over r. Plug in those numbers. Square root 2 times gravitational constant 6.67, 10 to the minus 11th, Newton meters squared per kilogram squared. The mass is the same as the mass of the sun, 1.99, 10 to the 30th kilograms, and then divided by the radius, which is of the neutron star, 10 times 10 to the 3rd meters, and it's not squared in our case. You will find that the escape velocity needed to just barely escape the gravity of that star is 1.63 times 10 to the 6th meters per second. So that is the escape velocity. Let me know if there's any questions you have on getting that escape velocity. Now, if this were on the test, maybe you might be able to just use the equation. It really just depends on what the question's asking. If I were just asking you for the escape velocity, sure, just use the equation. But in my case, I wanted you to actually understand the principle behind what you're doing. So in this case, the main principle is the conservation of energy. apply the conservation of energy, understand that the potential energy goes to 0 at infinity because you were taking it infinitely far away to escape it truly, and that in the minimum case scenario, you have no velocity left over by the time you've escaped it. You've just ran out of fuel at that time. So if you understand all that conceptually, then you're in good shape. Shouldn't you use some type of limit to come up with the potential energy final being equal to 0, or is it just conceptualized? Yes, you are taking a limit. So what I am saying here is that in the limit as r goes to infinity of this expression, minus g big M prime little m over r, as you take that limit, it approaches 0. And that's because you're essentially doing some number over infinity approaching 0. Any number over infinity will give you 0. So yes, that's essentially what you are doing. Is this going to be posted later? It's posted right now on the Dropbox link I gave you. You can check if it's on the Canvas page. If someone wants to confirm if it's on the Canvas page or not, let me know. But otherwise, go into the description box below this live stream video or to the top of this chat log, and you will find the Dropbox link for both the blank copy and the solutions. And there will be a third version by tomorrow as well. Awesome, it's in the Canvas. Cool. Any more questions before we move on to the next question? This will be the longest of all the problems because I put 5 parts into this, so treat this one like 2 problems in a way. So the rest of these problems are a little bit more straightforward. The first one is probably the most challenging, in my opinion. But the rest of these should be a lot more straightforward, and they're a little bit more familiar. And I've tried to, again, include most of the concepts, the main concepts in the class. So in tomorrow's last version, which should be posted sometime in the morning, with the solutions. In that version, I will try to cover any remaining main concepts that I have not touched on in these 2 practice versions so far that you've done. All right, so I think we're good so far on that. So let's move on to the next question. 2. Water flows through a river of constant depth such that it flows with an average speed of 5 meters per second. Assume no losses to friction. I forgot to revise this one on the numbers, so actually I'm going to send an updated version of this. I think the Dropbox link is correct. I'm going to be using 10 meters per second instead. Just a note on that. Let me see, make sure that I'm actually using... on the Dropbox version, is it 10 meters per second or is it 5 meters per second? Oh, it's okay, so it's still 5 meters per second. So I'm going to fix that after the live stream. So for now, use 10 meters per second. The reason being has to do with the calculation not being possible. So let's use 10 meters per second here. And I also needed to cut the height in half from 2 to 1. So we're going to use 10 meters per second, and we're going to use 1 meter for the second part. Okay. So in this one, we assume an average speed of 10 meters per second. If the river widens to 2 times the original width, what is the flow rate in this part of the river? Flow rate, I'm actually asking you for the speed. Actually, 1 second. How fast will the river flow here? actually remove this part of the question. So I'm just asking for how fast it's flowing. So let's take a look at this one. So let me write out the changes that I am making to the problem to make it possible to do, and we'll go from there. So the changes to this one will be that the initial speed, I'll call it V1, is 10 meters per second. And then I just want to know what the speed is. So what is the speed after the width cuts in half, not cuts in half, expands by 2. So this is an example of the of a liquid or fluid that's flowing, and then the diameter, like of a pipe, or in this case the width of our river, expands or contracts, causing it to either speed up or slow down. So what happens is, in here, if you look at this from the top view, you have that the river starts out initially narrower, and then it widens out to 2 times its original width. Now, so because I tell you that it's a constant depth, the area that the water passes through, which is what you really care about, that cross-sectional area here and here, cross-sectional area will just go with what the width is doing. So if the width is doubling, then so will the area in our case. Now, we write that this is area 1, this is area 2, which is 2 times area 1. And we have that the speed, the flow, V1 is 10 meters per second. And we want to find what V2 is. So V2 equals what? So there's one main concept you should know in liquids flowing through whatever your situation is, pipes, rivers, is that the flow has to be conserved. So whatever flows into this has to be what flows out of this. So flow in equals flow out. And the general principle, or I guess equation we use for that, is the equation of continuity. And we write that the equation of continuity is A1 V1 equals A2 V2. This basically says that what you have flowing in equals what you have flowing out. If you really wanted to be technical here, you would also write the density in this equation. But the reason why the density doesn't appear in the equation is because it's water. The liquid is largely incompressible. We regard it as incompressible so that the density stays constant and it just cancels out. So we don't even worry about the density. But flow in equals flow out. And I want to solve for the velocity out. So I'm going to solve for V2. V2 equals A1 over A2. That times V1. In here, you can just plug in what the ratio is if you already know the ratio, which in this case you know it's cutting in half. Or you can substitute the relation that you understand, which is that the area is 2 times the original area, and you can just drop that into that equation. So what will happen is the areas just cancel out in the end. So V2 equals A1 over 2 times A1, which is what our area at 2 is, and times our initial speed of 10 meters per second. 10 meters per second. And that's just going to be A1 canceling here. And it's just 1/2 of 10, which is 5 meters per second. So V2 is 5 meters per second. So you widen up the river twice as much, assuming the depth stays constant, and then the velocity ends up cutting in half as a result. Likewise, if you were to like take a hose, if you were to squeeze the hose, so you're constricting it, if you were to decrease the area, then the water has to speed up to compensate. So this is exactly that, but in reverse. Good on questions? Part B. After the river has narrowed down, it then runs uphill, rising through a height of, I'm changing it to 1 meter to make the problem possible to do. The reason being is that you end up getting an imaginary number in a square root if the situation is not possible, which it wasn't. So we're using 1 meter. How fast will the river be flowing at this point, referring to after it goes uphill? So at this point, so think of this problem as, okay, so you have let's say you have a blob of water. Okay, there's a random blob of water sitting in the river. Let's say that random blob of water is just, let's just say it's a ball with some mass, and all you're doing is you're just bringing it up to a higher location. So that problem you could solve with conservation of energy, or even kinematics, really. Now, because you would use conservation of energy to figure out, how fast would it be going once it rises through some height? Well, for a fluid, we just do it per volume. So there is a special equation for that, which is Bernoulli's equation. So Bernoulli's equation is the conservation of energy for fluids. So Bernoulli's equation which is just really conservation of energy, says that we have, I'm going to write it with 2 and 3 because in the previous part of the problem I did it from a point 1 to a point 2. What we're going to do now is we're going to go from point 2 and we're going to go up to point 3. So 2 will be my initial and 3 will be my final. So P2 plus GY2 plus 1/2 rho V2 squared equals P3 plus rho GY3 plus 1/2 rho V3 squared. So when you analyze this equation, this is where the conservation of energy is just cleverly hidden, is you'll notice that, for instance, the rho gy term just looks like mgy or mgh. That's potential energy. So this one's potential. The 1/2 rho v squared term looks like 1/2 mv squared, which is the kinetic term. And the pressure is actually just the work done, really, per volume. So this one's just based on the work done. So this is all just conservation of energy. Now, in our problem, we have the river flowing at 5 meters per second initially. The river has already widened, and all it's going to do is go uphill. So we have that, if I want to kind of draw like this, almost like this pipe as your analogy to a lot of the problems that they do with pipes and flow through the pipe. The width of the river stays constant the entire time, so it's analogous to saying that the diameter of the pipe stays the same, the cross-sectional area. Now, on this end, which we're calling 2, and this other end, which we're calling 3, initial to final, we have that the velocity initial, v2, is 5 meters per second. We know that we are raising it through a height of, in my correction, it's going to be 1 meter. So the height rises 1 meter. And that's your delta y. Okay. We're going to treat the bottom level as y equals 0 down here. The other thing is that the situation on both ends, other than you increasing its potential energy by raising it up, the pressure stays the same. Both ends have the same atmospheric conditions and the same depth. The pressure on both ends are the same. So we say that the pressure 2 and the pressure 3 just drop out because P2 equals P3. So now with those canceled out, all you have left are 2 terms on both sides. And now you have something common to all of them. The thing that's common to both sides at this point is the density of the water. If you did not cancel out the pressure, then you would not be able to cancel out the densities because it doesn't appear in every term and you can't factor it. But in this case, since the pressures are gone because they're equal on both ends, we could just factor out all the densities and get rid of it all. So now I will rewrite this without all the densities since it cancels. We have left side is gy2 plus 1/2 v2 squared equal to the right side, which is the same thing but for 3, gy3 plus 1/2 v3 squared. So once I've cleaned this up, I just want to solve for what the speed is after it rises through the height, so I just need to solve for v3. I'm going to collect this term over and group it with the other gy terms. So it's gy2 minus y3 when you subtract the term over and factor it, plus 1/2 v2 squared equals 1/2 v3 squared. Multiply by 2 to both sides, and finally square root it. So therefore, v3 is square root of a bunch of stuff. Distribute the 2 to everything is 2g y2 minus y3 plus 1/2, which gets canceled out by the 2. So it's just plus v2 squared. So now we've solved for v3. Plug in the values. Now you could either for y2 and y3, you could either set your y2 to 0 and just say y3 is plus 10, or you could just realize since you're taking the difference, but in the difference realizing that you're doing final minus initial, you're going to do 10 minus 0 in this case, so you will get 10. I'm sorry, 1 minus 0, so it's 1. Now, in the other version, I actually had that this was going downhill instead of uphill. In that case, you would have ended up lower than where you started, and your displacement would have been negative instead of positive. So either way, this is just the displacement. So it's 2 times 9.8 meters per second squared. Wait a second. If we're doing y2 minus y3, y3 is 1 meter and y2 is 0. So actually, based on the way that I moved it algebraically, it's actually going to be negative. So I'll just write it out. Y2 is 0 minus y3 is 1. So the algebra is indicating to me I'm actually plugging it in the other way around. So that ends up yielding a negative answer. And then plus the original speed, which was 5 meters per second. And then don't forget to square that. The reason why I changed the numbers in the first place was because of this. So if you get too big of a negative number here, it becomes imaginary, so it's not possible. So you calculate this out, and you find that the final speed after going uphill ends up being 2.32 meters per second. So this is an example of how to apply Bernoulli's equation, which is basically just saying I want to use conservation of energy in this scenario to solve it. So let me know if you have any questions on this part of the problem, how to use Bernoulli's equation, or anything regarding fluids. Yeah, once in a while the video lags on the live stream, just very occasionally, so you might get it for a little bit. Hopefully it's not lagging anymore. Is it still lagging? Question. In the other version where the flow rate is given, do we take this same approach? Yes. You take exactly the same approach on the other version. Now, the other version had the additional question of a flow rate in kilograms per second. The thing you should understand on that is that the flow rate stays constant. So if the flow rate was, for example, 75 times 10 to the third kilograms per second, so how much mass per time, whatever that number is, it stays constant. So the flow in equals the flow out, it stays the same number after. Now, as for when I ask you for the final speed, you would use the equation of continuity, which is based on the flow rate staying constant. So A1 V1 equals A2 V2, and that definitely still applies to the other version. Any other questions? And hopefully that makes sense. No problem. Okay. Looks like we're good. Number 3. Two vehicles drive towards each other on a narrower highway, and one of the vehicles swerves in front of the other, leading to a head-on collision. Assume one of the vehicles was a large big rig truck with a mass of 10,000 kilograms, traveling with a speed of 10 meters per second, and the other car, or the other vehicle, was a car with a mass of 1,500 kilograms, traveling with a speed of 20 meters per second. It is found that the car moves away from the collision with a speed of 5 meters per second in the direction that it was originally coming from. I want to know what the velocity of the truck after the collision is. So with this one, this is a conservation of momentum problem. Any collision problem practically is a conservation of momentum problem. So we're going to apply the conservation of momentum to solve this problem. The difference between this and the first version is that I actually give you one of the speeds after the collision, and you're just solving for the remaining one, the velocity rather. So problem 3. Problem 3 has that, so here's your two masses, M1 and M2. And the initial situation is that they're heading towards each other. So we say that this one, V1, equals, we gave that as 10 meters per second. And the other one was traveling faster with a speed of V2 equals 20 meters per second. So I have both of the masses and both of the initial speeds. Now, this was initial. The final situation is that now I don't know exactly what the truck is doing, M1. I don't know, but I do know that the car moves away from the collision in the direction that it originally came from, so in other words, to the right, with a speed of 5 meters per second. So the two final is 5 meters per second. these two velocities initially are would be v1 initial and v2 initial. So I don't know what v2 final is, and I want to find what that is. So we will use the conservation of momentum. And the conservation of momentum states that the total momentum in the system initially equals the total momentum after. So m1 v1 initial, which is the momentum of 1 initially, plus m2 v2 initial, the momentum of 2 initially. That gives us the total momentum of the system initially, and that's going to be equal to the same thing final. So m1 v1 final plus m2 v2 final. Now in this case, nothing is 0, so I can't just cross out anything. I have to just solve it around. I'm going to focus on solving for this term here, so I can solve for v1 final. So m1 v1 final, once I solve for it, is going to be, just take this term, subtract it over, so it's going to be m1 v1 initial plus m2 v2 initial minus the term I've moved over, which was m2 v2 final. Now, I could just simply divide over by the mass. I will actually just move it over at this point. So I'll just divide off by m1, and that will solve for v1 final. Now, if we plug in the values, because at this point we have everything, let's just plug it in. We have v1 final equals first term m1 v1 initial, so m1 is the truck, which is 10,000 kilograms. v1 initial is 10 meters per second, plus the which is m2, which is the car, 1,500 kilograms. v2 initial is, so the speed is 20 meters per second. And then the last term, we're going to subtract that. So minus m2, which is the car, so 1,500 kilograms. And we said after the final speed was 5 meters per second. All of this gets divided by mass 1, which is the truck, so 10,000 kilograms. Okay. Now, when you do this, if you were to calculate the answer as I do have it right now, it would not be correct. The reason why it would not be correct, despite your best efforts to plug in every number that I gave you, and there's not much to it, minus signs are always the worst enemy in physics. There's a minus sign on the 20. And the reason why is because these are not speeds, they're velocities. So how do you account for this moving to the right and that moving to the left? Well, left in this case is minus. One of them has to be a negative velocity relative to the other one because they're heading in opposite directions. So I'm going to say that in the standard coordinate system, in this problem, positive x points to the right so that v2 initial is negative 20. So the direction's now accounted for. The rest are positive because m1 was heading to the right, so it's positive. And m2, after the collision, goes to the right because it goes back in the direction that it came from. So that's also positive. So now, with the direction accounted for, that's going to yield us the right answer. With that, the answer that we get for this is that v1 final, in other words, the final velocity of the truck, equals positive, I'll emphasize the positive here for a reason, positive 6.25 meters per second. Now, the positive, or if it was negative, but in this case it is positive, the sign represents the direction of travel, because in here we are accounting for directions. So the answer is also directional. So plus implies moving to the right. Okay. So if I end up getting a negative velocity at the end, it would have been to the left. So this was just a simple conservation of momentum, just moving around, solve, and plug in the numbers. Worst enemy will be your minus sign. That will be the most common mistake in this problem. So pay a little bit more attention to your minus signs. Let's see here. Yes, the answer to the question, if the video gets posted after the stream, yes, it automatically does it. However, it does take a couple of hours, 2 to 3 hours, depending on the length of the live stream. So let's just say if the live stream ends with a total of 2 hours for the stream, then give it about 2 hours before it's uploaded. It will be in the video section of the of my channel. So if you go below the live stream video, you'll see the description, and you'll also see my channel. Go to my channel into the videos, and it should be posted there in about 2 to 3 hours, give or take. Else, if you wake up in the morning, it will be there. Now, we found the velocity of the truck after the collision. Let me know if you have any questions on that part. Last part of this is I want to know what the change in kinetic energy of the car is, just the car. In the previous version, I asked for the change in kinetic energy of the system, or at least something related to it. So here we're only going to care about the car. So now, to get the change in kinetic energy of the car, all I need to know is, well, change is final minus initial. So I'm going to do the final kinetic energy minus the initial kinetic energy, and that will be the simplest route to take if you can do it. In this case, you can. So the change in kinetic energy of, in this case, we're calling the car 2, object 2, is K2 final minus K2 initial. Whenever you're solving a problem, always, always, always attempt to see if you can do it the easiest possible route. In the case of calculating a change in kinetic energy, the easiest thing you can do is just ask what the change is. It's always final minus initial. If you have both, then do it. There may be other equations, such as, the work energy theorem says the total work done equals the change in kinetic energy. It's actually not that difficult to do that. It's actually very elegant. But a lot of times in physics, you'll have multiple equations or multiple routes that you can take to reach your solution. And the thing is that you always want to try the simplest route. And then once you take a look at that, you should also consider, what kinds of quantities do I know and how do they tie into what I want to know? But don't make it any harder than what it should be. So always try the simplest route first. Now the kinetic energies are just translational, so it's 1/2 mv squared. So 1/2 m2 v2 final squared minus 1/2 m2 v2 initial squared. That's it. Now we have both velocities. It turns out it doesn't matter that they're velocities if they're going to the right or to the left, because you're going to square it anyway. So really it just becomes the speed squared. You plug them in. Now you could actually factor this if you want to clean it up a little bit, because the 1/2 m2 is common to both terms. So you could just simplify your calculation just a little bit by factoring it. Okay. Plug those in. 1/2. Mass of the car is 1,500 kilograms. The velocity, initially, you could just plug in as minus 20 meters per second. Of course, when you take that number and you square it, remember that the minus sign will get squared out, so the minus sign is not relevant at all. And you're subtracting off v2 initial squared, which is 5 meters per second squared. Another common mistake that happens here is if the velocity is negative. So let's suppose that in my problem I had negative 5 meters per second. That ends up getting squared. A good percentage of the time, the mistake that people will make is keeping the minus sign outside of it and then doing things with that minus sign, which end up just getting the wrong answer. That's why I'm saying here, don't even care about the signs. If you just want to plug in the speed, then that's all the power to you. Okay, so ignore the signs on those. Subtract those two quantities. Delta K2 ends up being, after you calculate it, minus 2.81 times 10 to the 5th joules. Now, a question you might ask is, well, okay, I'm calculating a kinetic energy. Why is my kinetic energy negative? I mean, I'm squaring things, right? So if I calculated 1/2 mv squared for anything, I'm never going to get a negative kinetic energy. But I'm not calculating just the kinetic energy. I'm calculating the change. So whenever you calculate a change in anything, you can increase or decrease that value. So in this particular problem, when I ask you for a change, the minus sign in here represents that you've lost something or you've decreased. So this is a loss in kinetic energy. Pretty straightforward calculation. Let me know if you have any questions on this problem, and we'll move on to problem 4. I think we're relatively good, so let's keep on going. Okay. Number 4. A popular roller coaster ride immediately launches riders in a cart with a total mass of about 2,000 kilograms from rest very quickly up to a high rate of speed to go through a loop with a radius of 10 meters. We can model the horizontal section of the roller coaster like a spring system, which has a spring constant 500 newtons per meter and is initially compressed over a distance of 50 meters. We're going to assume that the y equals 0 at the bottom here. In this problem, I didn't need to tell you that. You should probably set the y equal to 0 at the bottom just to make it easier to calculate. And we're also assuming the track is frictionless. Now, we're going to figure out first how fast, in other words, what's the speed of the cart once it is fully launched through the 50-meter distance. So in other words, once the spring unravels, uncompresses through these 50 meters and the block or the cart ends up at the bottom of the loop, I want to know how fast it is going there. So this problem is a conservation of energy problem. So we're going to apply the conservation of energy. And this is one of those more realistic or everyday experience problems. So I guess even if you haven't gone on a roller coaster, the numbers that you should be getting for this kind of problem should be relatively reasonable. So the speeds that I'm giving you and such are all speeds that can be easily achieved, such as like when you're driving a car, etc. So for problem 4, I'll replicate the picture really quick here. So there's this point right here where we start, and I'm going to label that initial point as point A. Then I'm going to go 50 meters out. I'm going to reach this point at the bottom of the loop, call that point B. Okay. I'm going to find out what the speed at B is first, and we'll go from there. Now, there's also going to be a point C that we're going to involve in the problem, but we'll discuss that after this part. Now, in part A, I'm going to relate the information about what's happening initially to what's happening finally, A to B, and I will use the conservation of energy. So the kinetic energy at A plus the potential energy at A equals the kinetic energy at B plus the potential energy at B. Now, we also know that in this problem there is no friction or any other non-conservative forces that are doing any work in the problem. We are just going to have that this spring uncompresses and then launches it. The spring is conservative. Gravity is also conservative, so when we rise through the height in this loop and there's gravitational potential energy, gravity is conservative. There's no other forces that are driving this problem that contribute to any work done on that mass as it goes through this process. So we can jump straight to saying that the total mechanical energy to start with is just equal to what it is to end with. If there were non-conservative forces doing work in this problem, you would add in a work done by non-conservative forces term in here. So now, in here, we're going to say, okay, to start with, we're launching it from rest. So there is no movement initially, so the kinetic energy is based on movement, so there's no kinetic energy. Velocity initial is 0. We do have potential energy. There are two kinds of potential energy to consider in mechanics. We have the spring potential energy, and we also have the gravitational potential energy. But in this case, we are at the floor, so there's no gravitational potential energy. There's no height off the y equals 0. But the spring is compressed. It has the ability to do work on that mass and move it to point B. So therefore, there is potential energy stored in it. So we do leave that term alone. In the final situation, the spring completely uncompresses. So by the time it gets to B, the spring uncompresses completely and there's no potential energy stored. So the potential energy at B is 0 because the spring compression X is 0. So we have the initial potential energy in the spring is 1/2 K, which is the spring constant K, which I'll write a little bit differently. The compression X squared equal to the kinetic energy, which is 1/2 M, V final, which is VB squared. We can cancel out the 1/2s, and we're just going to solve for VB. So VB ends up being the square root of K, the spring constant, X squared over the mass. So you solve for the speed at point B, plug in the values, 500 newtons per meter times the compressional distance of 50 meters divided by the mass attached that you're moving, which is 2,000 kilograms, and the speed at B ends up being 25 meters per second. So we achieve a speed of about 25 meters per second, and if you want that in miles per hour, it's close to 60, 65 miles per hour. So it's a reasonable answer that we can expect for this problem. Now, once we have gotten the speed here, I want to consider a new part of the problem where I'm going to now consider what happens at the top of the loop. So that's going to be the next part. I'll label this point at the top of the loop C. And let's take a look at what we're going to be looking at for the top of the loop. Let's see. You said from the last part on question 3, are we supposed to know by our own intuition that it's negative? Let's see. On question 3, and you said the last part. Yes, you should. Well, now you can have, for instance, okay, so let's go back to this other question real quick before we move on to the next part. In this last part of this collision question, now I'm asking for the change in kinetic energy, so what you should intuitively understand is that the change can be either positive or negative. However, depending on the situation, it's either a gain or a loss. Now, for any individual mass, in this case, I am asking for an individual mass, which is the car. For an individual mass, you could have that its kinetic energy increases in the end. So, for example, if the car started from rest and then the collision happened as the truck moved it out of the way, then the kinetic energy of the car would increase because it would have to go from rest up to a rate of speed. So you would get a positive answer. But in our case, it starts out with a faster speed and then it loses speed. So that means we will get a negative change in kinetic energy or a loss. However, when you are doing a collision problem and I ask you what happens to the entire system, in other words, what's the change of 1 and 2 together, you can only have losses when you are considering the system as a whole. That's it. At best, you would have no losses, but you would certainly have no gains from the collision in total. So, refer to version 1 for what I mean about the system's kinetic energy decreasing. So take a look at version 1 for that otherwise. Hopefully that clears it up. Let's take a look at the last part of problem 4, which is pertaining to the top of the loop. So here's what we want to figure out. What is the minimum speed required to get through the top of the loop? So I do give you a little hint here in case it might not be obvious, but this is one of those things that you ideally should know after doing a number of problems. But I do give you the hint nonetheless for how to get that. And then I also ask, will the cart make it through the top? That's a yes or no answer, but you will need to figure out through calculation if it makes it through the top. So there's going to be some minimum speed that you're required to have to get through the top, and if you don't meet that minimum requirement, then you won't get through the top. So we're going to find out first what that minimum speed is, and secondly, we're going to find what speed we would actually have at the top and see if we satisfy that requirement. So let's take a look at that. Hopefully the stream is not lagging quite as much, but at least it'll be replayable. So okay. So now point C. So still problem 4. Part B. The minimum velocity to get through the top here, actually let me go back to the hint. The cart would just barely lose contact with the track at the top of the loop, assuming that it wasn't attached. Now in real life it is attached. But if it wasn't attached to the track, then it would lose contact with it. So this is the hint here. Now, losing contact should remind you of what are called contact forces. Forces that only arise when you are in contact with any surface. In other words, if you lose contact, then you basically have that these special forces will be 0. there are two contact forces. So let me write this out. Now, at this point C, so we have that there are certain contact forces, and our two contact forces are going to be one, friction, which acts parallel to the surface, and the normal force, which acts perpendicular to the surface, or actually the term they use in mathematics a lot too is the word normal. Normal is a synonym for perpendicular, so it is the perpendicular force. Now, if I am arguing that the cart will just barely make it through the top, in other words, at the very top, it just barely loses contact for a split moment and then regains contact, okay? At the moment that it loses contact, these equal 0 at no contact. Okay. Now, actually, even if you had contact, as long as you're not pushing into the surface or rubbing along it, then you wouldn't have a friction or a normal force anyway. But certainly when there's no contact, you won't have those forces because they're contact forces. Now, I'm saying this because when you solve this problem, you need to say that, you know, if you were involving these, that one of these is 0. So we know we already have no friction in the problem, so what I am saying is that there is no normal force to consider. So to solve this, you must realize that it is a circular motion, and there are forces acting on it to control its motion. So in circular motion, the sum of all forces in the radial direction along the radius of the circle, also written centripetal, equals mass times acceleration in the radial or centripetal. Now, we're going to write our sum of forces, but the one key point to remember with circular motion and your coordinate system is that you're going to assume that anything that points towards the center is taken to be positive. So anything that points towards the center, we will take as positive. So if it's at the top, if it points down, it's positive. If it's at the bottom and it points up, it's also positive. So with that said, when you consider your forces, you have your weight, mg. Now, technically, if I draw it in, because when you do the free body diagram and you assume, okay, so it's in contact with the track, there would be a normal force. So the thing is that if you think of it as, okay, you see at the bottom, something almost pushes down to the track, so the normal force points up. But the thing is that the normal force will continue to follow the orientation of the surface. So if the normal force points up at the bottom, it's going to tilt as you go through the circle. It's going to be angled. Then it becomes horizontal, but then it goes upside down. So in a sense, you're pushing up into the track, so the track pushes back down, and there's a normal force that points directly downwards at the top. Now, that will be the full free body diagram for that, but go back to this. We're considering that the normal force is 0. So while you want to process that there is a normal force in the diagram in general, we're saying that it loses contact, so we're going to set it to 0. So when I write out the sum of forces, they both point down, so they're both positive in this coordinate system. So in other words, the normal force plus mg equals the right side, which is m, and the acceleration in the circle, the centripetal acceleration, can always be expanded out as v squared over r. So we write v squared over r. We will get rid of the normal force since it loses contact, so no contact. And when you solve for this velocity under this no contact condition, you will get the minimum speed that's required to get through the top. For that brief moment at the top, it just barely loses contact. So v, when you solve for it, you can cancel out the masses, multiply by r, and square root it. You'll get the square root of gr. From here, plug it in, 9.8, and the radius. The radius is given 10 meters, and you'll find that this speed is 9.9 meters per second. So that will get us the minimum speed to get through the top. Now, once you have this minimum speed, I want to know, does it make it through the top? So do I meet this minimum requirement? So emphasis, minimum. Okay. So if my speed is less than 9.9 at the top, that means I would not have made it. It needs to be equal to or greater than 9.9 meters per second. So here's how we're going to do that. We know information about point A and B, and at this point we could just use a conservation of energy to link it to point C and then solve for the speed at point C using conservation of energy. So we repeat conservation of energy. You can do either point A or point B, it does not matter. I'll just use point B. So, from B to C, I'm going to write KB plus UB equals KC plus UC. Total energy initial equals total energy final. There's no non-conservative work to consider. So, go through this. There is motion at point B at the bottom. We expect there to be a speed down here, so we do have kinetic energy. We have no potential energy at the bottom because certainly the spring is done uncompressing, so there is no spring potential energy, but also there's no gravitational potential energy because it's not gained any height yet. So that's gone. Now, there is allegedly motion at the top, so we're going to assume there is kinetic energy. Potential energy, we do have one kind, but it's not the spring because the spring's no longer involved after point B. We've risen through a height, so we will now use the height of the loop, which means we have gravitational potential energy, so we do have that. We write this out, so we have 1/2 mv initial squared equals 1/2 mv final squared plus mg y final. We want to know the information at the top of the loop for its speed, so we're going to solve for VC. So, when we solve for VC, after you move this term over to the left side and you isolate this and cancel out all the masses, so the mass again doesn't matter here, you get that VC is the square root of VB squared plus, actually it's minus M, which cancels out, so it's minus GYC. Okay. And then when you multiply by 2 to everything, the 1/2 is gone and you get a 2 here. So again, move this term over and multiply by 2 and take the square root. So once you get that, plug in the numbers for this. So 25 meters per second squared minus 2, 9.8 meters per second squared times the height of the loop, which ends up being the diameter of it. It's not the radius, so it's 20 meters. Plug that all in, and you get the speed at the top of the loop ends up being 15.3 meters per second. And 15.3 meters per second is larger than the minimum speed, which is 9.9 meters per second. So we make it through the top. Okay, so if for some reason the cart was not attached to the track, which would be pretty scary. We are going fast enough to make it to the top of the loop, and you would come back down along the track, so you'll be fine. Realistically, though, if the roller coaster were to not go fast enough or stop at the top of the loop, it'll just sit there. It sits in place for safety reasons. But in a typical physics problem, we assume it's not attached. So in this case, we do meet the minimum requirement to make it through without any other safety mechanisms. Let me know if there's any questions on this, and then we'll move on to the next question. Any questions, assuming that the live stream is not lagging. So. Cool, got better. All right. I'm getting closer to the end of this, so looks like we'll finish it in the next 15 to 20 minutes. So, problem 5. This one is similar to the last version, however, I am doing something different with this question. You'll see the differences in this version. So, a 5 kilogram mass sits on a frictionless, that's the first thing that's different, on a frictionless horizontal tabletop. A string connects from this mass over a light frictionless pulley and to a hanging 2.5 kilogram mass. Assume that the string is initially 200 centimeters long from the 5 kilogram mass to the pulley. So from the location of this mass on the tabletop all the way to the pulley, that's 200 centimeters, or in other words, 2 meters of length initially. Assume that that has a total mass of 20 grams in that section. So I tell you the total mass and the total length in this section right here. First thing is, what is the acceleration of each mass? Okay. There is one thing that you will assume in this problem, which you'll kind of see makes sense here, is that the mass of the rope or the string is much, much smaller than the masses that are driving the system. So we're going to ignore that the mass of the string contributes anything to the motion of the system. But you'll see later why this will matter. For the time being, ignore the string having a mass and a length that we need to consider, and we're just going to ask what's the acceleration of each mass. Now, typical pulley problem. So we just use Newton's laws to solve this. So, and the pulley problems follow a general strategy or general pattern. So let me outline what happens with this. So here is the horizontal tabletop with the mass, call it M1 on the top, the string, the pulley, which we don't care about, it only changes the direction of the string, and then a mass 2 that hangs vertically. Now, draw the forces on it. So the weight goes down. The normal force goes up, but the normal force does not always go up. It always goes perpendicular to the surface. So in the horizontal surface, it is straight up. But if you have an incline, a tilted surface, or, you know, the extreme case is a vertical wall, like I push into this wall right here, it pushes back out horizontally. That's the normal force. So the normal force is not always up. It's always perpendicular. Now, there is a string or rope, so there is a tension, T, that points away from the mass and along the rope, always. Now, there is no mass to consider in this pulley. There's no moment of inertia. We do not consider the rotation of the pulley. So, long story short, the tension here is going to be the same tension over here, but just in a different direction. In this case, the tension on mass 2 is up. There's no friction in this problem, so there's no friction to draw in anywhere. And we lastly have the weight of this mass going down, m2g. So we have two different weights. Make sure you write m1 and m2 times g, because if you leave off the 1 and the 2, you'll accidentally cancel out the masses somewhere. Now, once you have this set up, so this is your two free body diagrams, draw the coordinate system. So this one's intuitive, positive x to the right, positive y upwards. But remember that the coordinate system will follow the motion of the system. So since the system tilts in a different direction, you need to tilt the coordinate system so positive x flows to the right, but it turns 90 degrees clockwise to mass 2. So the coordinate system is now positive x downwards and positive y to the right. I'm not going to care so much about the positive y being to the right, but I will care about positive going downwards. The most common mistake here is to accidentally put positive upwards inconsistently with the positive going to the right here. So notice that positive for the entire system must flow one direction along the string continuously. If positive were to point upwards here, it would clash with the other positive direction. So the point is to be consistent. Make sure the positive flows one direction along that entire string. Okay. Now, you could alternatively put positive upwards, but that would need to mean that positive would have to be to the left on the other one. So be consistent. Now, in this problem, you want to find the acceleration of either of the two blocks. They will be the same magnitude of acceleration because they're attached. The motion of one controls the motion of the other. They are bound together, whether if they like it or not. Now, the length of this string is not ever going to change, and that's the reason for why they have to do everything together. So their accelerations will be the same. Their speeds will be the same. The distances they move will also be the same. So if I ask you for the acceleration of 1 or the acceleration of 2, they're the same. Now, given that I can find the acceleration of either mass and it solves the problem, let's just pick a mass to solve. Now, again, going with the philosophy that you ideally want to make your life as easy as possible, in this case, I mean, this mass 1 has less forces acting in the direction of motion, which is the direction of the acceleration. So in this problem, at least, I would initially consider attempting to solve it on mass 1 first, just because it looks easier. So now, direction. Solving for this acceleration solves the problem. But the problem is that when you, for instance, write in what your sum of forces are, there's only one force with an x component, which is the tension, which is in the positive x direction. So you write positive tension, just T, equal to, leave the right side alone. So that's it. Now, ideally, if I just divide off by mass 1, so I know the value of mass 1, which I do, and if I knew the value of the tension, I could just get the acceleration, I'm done. But the problem is I don't know what the tension is. So now let's go from here. So where else will we find the tension? Well, to get another equation for the tension, we realize that the tension appears on both masses. So we can just use the tension on the other mass and say, oh, well, the tensions are the same. So let's find the tension on mass 2. So in this problem, you do have to use both masses. We just tried to take the simplest route possible if it worked. But now we go to the other mass, mass 2. Repeat sum of forces in the x direction, which is in this case up and down based on the tilted coordinate system, equals m2ax. So again, write in the forces on the left side. So in our case, we have two forces along the x-axis. Now, most common mistake, again, is even if you write your coordinate system correctly, is a very fair chance that you're going to still accidentally write the forces wrong. Because most of the time, you're accustomed to positive going upwards, so you're naturally going to want to say, oh, it's the tension minus the weight. That's going to get the wrong answer because it's actually weight going down, which is positive, and the tension going up, which is negative in this coordinate system. So you have to write the weight positive and 2g, and then the tension negative, so minus t. So that will be the most common mistake, again, in this problem. Be aware of that. Equal to the right-hand side, so leave that alone. Solve for the tension that you needed to get the acceleration over here. So we are going to swap places here with these two terms. So the tension equals m2g minus m2ax. Take this tension expression and drop it in where you needed it. So now, write this in here. The tension gets substituted with this, so I will write m2g minus m2ax equals m1ax. Now, we've taken care of the tension, but we need to solve for the acceleration, realizing that there are two terms that have the acceleration in it. So all we need to do is group the two terms together. So we have m2g equals m1ax plus m2ax. Factor out the common acceleration, because they're the same, m1 plus m2ax. Then just divide off the remaining extra stuff. So in the end, therefore, the acceleration is, the only term left on the left side is the m2g. And we're dividing by m1 and m2. So we get this expression for the acceleration. Now, there are at least 2 or 3 different places that you can easily make an algebra mistake or a conceptual mistake. So when you do this, check the units. Checking the units only takes 10 or 15 seconds. If the units don't work out and give you acceleration in meters per second squared, then it's not right. So check the algebra if you don't get the right units. But in this case, you do get kilogram meters per second squared in the top, which is a force in newtons, divided by kilograms in the bottom, which just cancel out the kilograms, and it just gets you meters per second squared. So anytime you solve for an acceleration in this kind of pulley system, you're going to find that it takes the form of a bunch of forces in the top divided by all your masses in the bottom. So you plug and mix the numbers for the acceleration. So I'll just put ... here. This is mass 1 is 5 kilograms. Mass 2 is 2.5 kilograms. Just make sure you plug in the numbers appropriately, and the answer you end up getting in the end of this is the x acceleration is 3.26 meters per second squared. As far as a reasonable answer, this acceleration cannot be any bigger than the acceleration of gravity. And that's because the main driver of this entire system, the reason why this mass would drop and this mass would consequently move to the right, is because gravity is pulling mass 2 down. So if gravity is the only driver of the system, then gravity is supplying an acceleration of 9.8 meters per second squared. So this value better not be any bigger than what the main thing driving it is. Now, if I had any extra, pushes or pulls, me forcing things, that value could be anything bigger than 9.8 or whatever it is. But in this case, with only gravity driving it, you better get something between 0 and 9.8. So that's how we know in this case the answer is at least numerically reasonable. Who knows if it's correct if you make one silly mistake, but at least it's a reasonable answer. Let me know if you have any questions on getting the acceleration first before we move on to the other concepts that we're going to link to this. Okay. It's unfortunate that the stream quality is dropping or going out completely, but seems like everyone more or less is back now. So I'm going to go on to this next part with the tension, but let me know if you have any questions. To find the tension in the string, we already actually have the equation for it because we already did all of the derivation in the first part of the question. So what we're going to do to find the tension in the string in part B is I'm going to use all the equations I've written on the board for my Newton's laws, and I'm just going to realize that I already have a tension expression written out here. So as long as I can plug in the values here, I can just get the tension immediately. Now there's actually one other place I already have the tension, which is here. But if I had a choice between this longer expression and this shorter expression, I'm going to choose the easiest route possible because they are going to be the same answer in the end. So I will use the simpler expression for the tension, and I would just plug into that, and it will give me the answer immediately. So I use the 3.26 meters per second squared. So we have mass 1, which is 5 kilograms times 9.8 meters per second squared. Oh, sorry, not 9.8, that's g. I want ax, which is 3.26. So we plug in those values, and we get that the tension ends up being, and let's see, I believe I made one mistake in the solution because I'd accidentally plugged in 2.5, which is actually strangely enough what I did in the other solution. So if you put this together, you should get 16 point, that's going to round to 3, I think, newtons. Okay. So you get the tension for this part by just simply dropping it into the equation. Now, what I'll do is I'll probably I'll re-upload the solutions to this that are fixed. So this will be one of the fixes in there. Now, the next part is, let's see. And you have a question. How would we approach a similar question if the case was where you have a pulley with a mass? So if you have that the pulley has a mass in this question, you then do Newton's law a third time, but in rotation. In other words, do it with torque. So you would do all the things that I've done in this problem, but you would have a third equation with the torque on the pulley, and the difference is that the tension on one block and the tension on the other block will be different. So then you will have to call one of them T1 and the other one T2. And using the third equation with the torque, you can then relate the T1, T2 together and get rid of both of the tensions. So you do have to use the rotational form of Newton's law, which is sum of all torque equals moment of inertia I times alpha, the angular acceleration. that's hypothetically, which I'll probably do in the next version that I make actually. Now, this question right here, C. If the string is plucked so that the disturbance ripples down the string, how fast does that wave move? So this one is pertaining to a wave on a string. So there is an equation for the speed or the velocity of the wave on the string. So let's do that. Now, part C. The speed of a traveling wave on a string is v equals the square root of t over mu. T is the tension in that string, or that section of string, and mu is the linear mass density of that string. So mu is defined as the mass per unit length of the string. This is where the original information in the beginning of the problem comes into play, which is how much mass of string you have in that section and how much length you have. So in the beginning of the problem, I told you that the length of the string was, or the mass of the string was 20 grams, which is 0.02 kilograms, divided by the length for that section was 200 centimeters, which is 2 meters in standard units. So the linear mass density ends up being 0.01 kilograms per meter. Okay. So we have the linear mass density now. We just plug it in. So V is the square root of the tension, which is 16.3 newtons divided by 0.01 kilograms per meter. Calculate that out, which I believe is not correct on the solution because the previous part was not correct, so we're going to calculate that. So 16.3 for 0.01 is 100 times bigger, and then we're going to take the square root of that, and that gives us 40.4 meters per second. And that's the speed of the traveling wave on the string. Now, from that, the next part pertains to what happens when you know that velocity or speed, which is after 0.5 seconds of time has elapsed from being released from rest, so you let the system go from rest, how much time would it take for the wave pulse to travel the length of the string to the pulley? So I want to know how much time based on a distance that I'm going to travel and a speed that I'm going to travel, the wave in particular. So now, finally, so let's go over here. The length of the string is no longer 200 centimeters or 2 meters because I said that we are releasing the system from rest, and this will move some distance in half a second, whatever that distance is. But this length will be shorter than 200 centimeters, and we need to figure out how much shorter it is. So what we're going to do is we're going to figure out how much it moved by using kinematics. So you write out all of the kinematics quantities that you could possibly use. This is the displacement of that block. I don't know that. I release it from rest, so the initial velocity is 0. I don't know how fast it goes after half a second. I know the acceleration of the system is 3.26 meters per second squared. The time interval that it moves over is half a second. So, I have that it's half a second, and this is all the information relating to the half a second that that block moves to the right. I need to know how far that block moves to the right, because that's how much shorter that string gets. So I need to solve for that using a kinematic equation, which we could just use delta x equals v initial delta t plus 1/2 a delta t squared. I'm going to get rid of the initial velocity because it starts from rest. So it's just 1/2. The acceleration of the system is 3.26 meters per second. And the time is half a second, which we're going to square. Okay. That distance that you end up getting ends up being .41 meters. And so we're going to subtract that off of the total length, which is how much of length the string is going to be left after it's moved to the right. So this implies the length of the string after is 2 meters minus 0.41 meters. That gives us a length after of 1.59 meters. So now this is the distance we're going to consider that the wave pulse travels over. Now, of course, there would be the issue with the fact that technically the block continues moving to the right even while the pulse is moving. But we're going to assume that the pulse moves a lot faster than the block is, so we're going to assume that the length is relatively unchanged in that short interval of time. Now, the time that it takes to travel is just simply the distance divided by the speed of the wave. This is just velocity equals distance over time, but just rearranged for the time. And this is how much time it will take for the wave pulse to propagate the entire length of the string. So we have that it's 1.59 meters, and the wave speed was, that was not 28.6, I just erased it, so that was the square root of 16.3 times 100. So it was 40.4 meters per second. So we're going to use 40.4 meters per second. And that yields a time of 0.039 seconds. The time it takes to go from one end to the other is extremely small compared to the time interval we're working with. It's not even 0.03 seconds compared to the 0.5 seconds that has already elapsed. So the pulse travels very, very quickly. Let me know if you have any general questions on this problem. I'll let you look at it for a minute, and then we'll move over to the last question on this one. Let me know if everything's good otherwise. Actually, I'll leave it on this. Oops. How did I change back? Okay. This one might be a little bit more confusing because you might not have realized that the length of the string was changing based on the fact that the mass was dropping and bringing mass 1 to the right. So once you realize that the length of the string shortens by a certain amount, which is determined by the displacement of mass 1 in that half a second time interval, once you realize that's how much string you lose on the top side, then you can say, oh, here's my new length of the string, and here's how long the pulse will take to travel that new length of string. So there's a little bit of kinematics involved with that. Beyond that, it wasn't too bad, but that's probably the most easy thing to miss there. Okay. With that, let's look at the last problem. So this one's a very, very straightforward problem. I didn't do anything weird with this one. This one, you should pretty much know very straightforwardly how to do this one as long as you know the right equations. So this one, we're going to consider a spring system which has a natural length of 50 centimeters. And it's stretched so that it is 80 centimeters after, so there's an initial length and there's a final length. The attached mass is released from rest. I give you that the spring constant is 500 newtons per meter, and the attached mass is a quarter of a kilogram. Given all of this, we're going to figure out these few things, and they're largely plug and chug. Give me the equation, plug it in. So first, we're going to determine the period and the frequency of the motion. So we're going to write the equations for those. Okay, so last problem. Six. Okay. So there's two things I'm going to mark out here in terms of positioning. This point over here represents how long the spring was to start with. So x equals 0 there. Okay, because x is used in a spring to represent the how much longer it got or how much shorter it got. How much did you elongate it or compress it? So here, no stretch, no compression. Its initial length was 50 though. Now here, the new length is 80, but that means we've elongated it by 30 centimeters. So x is 0.3 meters. Now, from this point, you will release the system and you will let it oscillate. So we are releasing it from its amplitude. It'll pass through equilibrium and it'll shoot to the other side, reach the other amplitude, come back, and repeat. It will just bounce back and forth between the two amplitudes, assuming no losses. So this is not a damped oscillation. It is an ideal oscillation. So first thing is the period, capital T, is 2 pi square root of m over the spring constant. Mass is given as 0.25 kilograms, and the spring constant is 500 newtons per meter. Okay. Okay, so when you plug in those numbers, you calculate it. The period is 0.14 seconds. Now you could also write the whole formula for the frequency of the oscillation, but the frequency by definition is 1 over the period. So all I need to do is flip it. Take the inverse, you get 7.12. It will be 1 over seconds, but that's also hertz. That's it for the first part, so just plug it into the appropriate equations. This factor here, the square root of m over k, or k over m, depending on your situation, is also omega for the system, the angular frequency, as we would call it. So we're going to be using omega repeatedly, so we'll be looking at what omega will be in the future parts, but keep that in mind when you're doing these, is that this is just related to omega. Now, the latter parts of the question, after the period and frequency of the motion, part B, what is the total mechanical energy of the system, and what points in the motion correspond to the maximum potential and maximum kinetic energy respectively? So first, the total mechanical energy of the system is going to be always kinetic plus potential energy. But you could use any point you want. You could always use the kinetic and potential energy at any point in the oscillation or whatever problem you're doing. However, I would say that there are unique points in which the total mechanical energy is easier to calculate, because you can actually say that one of the terms is 0 at these unique points. So, first of all, the unique points in the problem that you should know are equilibrium and the amplitudes. So, you of course have the amplitude on the other side, which is just negative that distance. But the amplitudes of the motion have maximum potential energy. So maximum potential energy, which is U. At the equilibrium, in exchange for all that potential energy that you've used up, you gain that amount of kinetic energy. So at the equilibrium, you have maximum kinetic energy. At either of those two unique points, here or here, you will have one or the other, not both. Because at the amplitude, you have 100% potential energy and no kinetic. At the equilibrium, you have 100% kinetic and no potential. So the idea behind this is that you could use one of these two unique points and you can calculate the total mechanical energy in the system, because all you're doing is you're adding 100% plus 0. So you just don't consider the other one. So the total mechanical energy of the system, call it E, is just 1/2 Ka squared. That's it. This is the 1/2 kx squared formula, which is just the potential energy. But notice that you are evaluating it at the amplitude of the motion, which is where you have all potential energy. So plug that in. 1/2 spring constant. And then the amplitude of the motion is 0.3 meters. Don't forget to square it. And for that, you get that the total mechanical energy ends up being 22.5 joules. So the total mechanical energy is conserved in the system, meaning that it does not change. So no matter which point I pick in the system, no matter how much I have is kinetic, and no matter how much is potential, they still add up to 22.5 no matter what in this system. So at the amplitude, I have 22.5 joules of potential energy, and at the equilibrium, I have the same amount in kinetic energy. From that, we're going to find the maximum speed the mass will move with in the system, and I'll actually do part D at the same time, which is the maximum magnitude of acceleration. They're also very, very simple equations if you know what they are. So C max speed is V equals omega times A. Now, this essentially looks like the V equals R omega formula, which is linear to rotational motion, but the amplitude takes place at the radius, basically. Now, omega is the square root of the spring constant divided by the mass. This is where you will need that again. This is the factor that keeps on reappearing in these equations, times the amplitude. You can plug in the numbers for that. The spring constant is 500 newtons per meter. The mass is 0.25 kilograms and the amplitude is 0.3 meters. And you'll get that V maximum is 13.4 meters per second. So this maximum velocity goes with a maximum kinetic energy, which occurs at the equilibrium. Now, on the other hand, the maximum acceleration in the system part D, the maximum acceleration is omega times A squared. So we plug in this again. So this, actually not omega A squared, it's omega squared times A, correction. So this is going to be the square root of K over M squared, which just ends up being K over M, times A, which is 0.3 meters. So plug in the same values, and you get that the maximum acceleration is 600 meters per second squared. And this acceleration does not correspond to where it's moving the fastest. It corresponds to the amplitude of the motion where it's actually sitting still. So just because it's not moving, it doesn't mean it doesn't have acceleration. It has to have acceleration. In order to get it to go from rest to a velocity, it needs to accelerate. So the acceleration is actually maximum at the amplitude where you are stretching the spring the furthest from the equilibrium. Let me know if there are any questions up to this part in the problem, and we will do the last part of the problem and the practice exam. All right. So largely with these, plugging into the correct formulas, I'll see if I can make another version tomorrow where it's not quite as simple as plugging into the formulas, but here is the last question of everything. What is the position, the velocity, and the acceleration when an amount of time elapses after release equal to 10% of the period? So with these ones here, you know what the period is, and you're just going to take 10% of it. And you just want to calculate what the position, the velocity, and acceleration is after that 10% of a period. This is just using the equations that correspond to how those vary with time. So here's what they're going to write out as. Okay. So keep in mind that you're taking the mass and you are releasing it from rest at the amplitude, and you start the stopwatch right then. Now, that means that whatever function follows from there is based on the starting position being at the amplitude. So for instance, the position function needs to start at a maximum, then go to 0. And that, if you were to plot it on a graph just real quick, starts at a maximum, goes to 0. This is a cosine function. So I'm going to use a cosine function. And it takes this form. Is that the position versus time is some amplitude of the motion, and it oscillates with a cosine function. Now, keep in mind here that omega we keep on using over and over again. Omega is just the square root of k over n. Now, if we just calculate this out, so we can just use it over and over, 500 newtons per meter over 0.25 kilograms. Where did I put that? Oh, here we go. Square root of that, 44.7. So I get 44.7, and we'll have 1 over seconds for the unit. That's what the angular frequency will end up as. Now, I just use that value in here consistently. Now, t will be plugged in as 10% of the period, or 0.10 times the period. So 0.10 times the period, we have that the period is 0.14 seconds, so that just ends up being 0.014 seconds. And that's the time we're going to use for all the functions. Now, in your other functions, they're just going to be a derivative of the previous function. So the velocity is the derivative of this, which is negative a omega sine omega t. The acceleration will be one more derivative with time. The acceleration is negative a omega squared cosine omega t. Now, you may realize that this term out front, a omega, and this term, a omega squared, are actually just the things we've calculated before, because a omega was the maximum velocity. That's why it corresponds to the velocity function. And a omega squared is just the maximum acceleration. So you don't even need to remember that. As long as you know the functions, the stuff out front are the maximum values of those quantities. So since I already know what those values are, I don't need to recalculate that. I can just drop in what the maximum speed is and what the maximum magnitude of acceleration there is. We will just plug in the values for these. So A is 0.3 meters cosine of omega 44.7 times t, which is 0.014 seconds. We're going to repeat that for here and for here, but A omega is V maximum, which is 13.4 meters per second, and A omega squared is the maximum acceleration, which is 600 meters per second squared. Once we plug in all these values to each of these functions, you'll get the position, the velocity, and the acceleration at any given time. So if we make a quick calculation for each of those, we'll get the answers to all these. X equals cosine 44.7, 0.014. Okay. Cosine of that times that, and then times 0.3, 0.29. Let me make sure I got that right. I'm getting about 0.29. It almost rounds to the same number. I'm going to quickly make sure that my numbers are correct because something doesn't quite seem right, that it's pretty much the same value. Square root of k over m. Yeah, my omega is right. And then the period was 0.14 seconds. So it's just 10% of that. So let's see, 0.25 over 500, square root of that answer, n times 2 pi. Okay, so everything looks right. That should be pretty much it then. So cosine of omega, 44.7 times 0.014, and then that should give me the answer, but oh, that's right, it's in radians, that's why. So when you plug in these values, the thing is that plugging in omega times t does not yield degrees, it yields radians. So when you do this, you have to either convert it to degrees, or I would just suggest putting your calculator in radian mode. But the thing with that is that you have to be careful that you have to switch it back and forth between degrees and radians. So when you put your calculator in radian mode, which is the proper units of this, and you take the cosine of it, then you get the correct answer, which is 81% of 0.3. You get 0.24 meters. Okay. The reason why I knew that something was not quite right was because 10% of the period means that this thing will have moved a reasonable distance towards equilibrium. The answer I was getting was suggesting that it didn't move at all. It was like 0.299999 compared to 0.3. That's practically nothing. That didn't make any sense. So since all my numbers were right, the only other thing was that plugging into the cosine function, it's got to be in radians. So convert it to, or change the calculator into radian mode, multiply it, and you get the correct answer, and that's much more reasonable for 10% of the period. Okay? So always make these checks of the reasonability so that you can see if the answer is close to right or not. Now, repeat this for the other ones, and we're going to get the following values. V equals, so we're going to do the same thing, cosine, but it's going to be a sine function, times 13.4, negative 7.85 meters per second, and the acceleration we'll do this one more time. Cosine times 600 meters per second squared, negative 486 meters per second squared. Okay. So now you get the position, the velocity, and the acceleration at this specific time of 10% of the period. So, for instance, the negative signs represent that it's pointing to the left. So, for instance, this velocity is still pointing to the left, so the block is moving to the left at this time. The acceleration is pointing to the left, meaning it's being pulled towards equilibrium, so it's still somewhere over there. So it also makes sense that it's negative. Let me know if there are any final questions on this problem. It's getting late, and then we'll wrap it up. Also, to be honest, running out of breath too. Okay. Any last questions? Or give me a thumbs up if everything is good, all is well. Get enough sleep before the exam. Try not to pull an all-nighter. All right. No problem. That looks like that's it. So I'm personally going to catch my breath because I'm a little out of breath from going continuously. But the next review session will be tomorrow from 12 to 2 in person. Come for another practice exam, some candy, and best wishes with all of your studying. Thank you for tuning in.